Hello, this is Mahanta Didia. This module is incorporated in the book on liquid formulations. The book categorizes liquid formulation as solution, suspension, and emulsions. These products are widely used by pharmaceutical, biotechnology, dermatology, and cosmetics. The scientific discipline employed in integrated approach of development of innovative products is the main focus of this book. An integrated approach is used by many innovative pharmaceutical and cosmetic institutions, from selection of excipients to lab formulation development to commercial scale manufacturing. And it is captured in this book. The subject matter sequencing is used in the book for each category of liquid formulations. And these are physicochemical characterization, pre-formulation, composition and formulation, lab scale and commercial scale processes, quality by design, and formulations used in clinical study. Modular format is further transformed into theme-focused subject matter so that the readers can access each module independently for their own learning and references. Each module incorporates video and animation that will help reader visualize the concept. In this particular module, we'll focus on physicochemical characterization of emulsion products. The theme of this submodule is physicochemical principle involved in composition of emulsions. Emulsions are made of immiscible liquids and emulsifiers. In a separate submodule, we'll focus on classification and type of emulsions. Immiscible liquid, let's start with that. Emulsion is a basic dispersion. The dispersed phase is composed of small globules of liquid distributed throughout the continuous phase or vehicle in which the dispersed phase is immiscible. That is, they do not mix. Substances that mix in all proportions in forming a homogeneous solutions are miscible. Miscible liquids are harder to separate as they dissolve in each other. And in order to separate, we use fractional distillation method if possible, where different boiling points exist. Immiscibility, liquids don't mix in each other in substantial portion. For example, oil and water. It's possible to shake this mixture and temporarily make a homogeneous mixture, but soon it will separate. And separating immiscible liquids is simpler to achieve than a miscible liquid. Let's look at this slide. In this slide, water is colored as a red to show the differences. And in the top portion, water is mixed with alcohol in different proportion, starting from 20 milliliter of water to 80 milliliter of water, and alcohol from about 80 milliliter to 20 ml. If we mix that, we'll see a homogeneous red color solution. Water and alcohol are miscible. If we look at the bottom of the same slide, we have 50 milliliter of water, again colored red, and 50 milliliter of canola oil, light yellow. If we try to mix them together, it will form two distinct layers. And this will be very visible. We are familiar with Italian dressing, which has oil layer and vinegar layer. We will look at the mechanism of miscibility and immiscibility in our next slide. The molecular interactions takes place in the liquid media for miscible and immiscible liquids. Let's look at miscible, that's on the right-hand side. In this case, sodium chloride, shown as a yellow and green crystal, is dissolved in water, water indicated by oxygen and two hydrogens. When water approaches sodium chloride crystal, it dislodges chloride and sodium ion due to hydrogen bond formation. As soon as an ion, either chloride or sodium, is dislodged, it's carried away and then it's surrounded by other water molecules, forming a very strong hydrogen bond. In this case, intermolecular forces of attraction between sodium chloride, a solute, and water are much higher than intramolecular forces that sodium chloride crystal together. Let's look at now immiscibility. In this example, we are looking at methane as an immiscible oil and water as a solvent molecule. And in order to put the charges, negative charge of water has -1 and hydrogen has +1 charge. So when we add quote oil, in this case methane, in water molecule are strongly charged with a plus and minus charge. Whereas methane does not have similar charge on its molecule. It's a nonpolar and it has a very weak delta plus and very weak delta minus. Consequently, in methane are very weak compared to solvent-solvent interaction in water through hydrogen bonding. As we mix this, water and methane will mix it, as you can see in a sample. And as soon as molecule starts moving, water molecules will attract towards each other, forming strong hydrogen bond. Essentially, water molecule squeeze methane and phase separation occurs. So in this case, physicochemically, the attraction between two liquids is much less. Let's look at separation of oil and water in this particular simulation. In this, olive oil is added to water mix. And you'll see small globule formation. However, the globules will float and layers will separate. If we provide mechanical energy, there would be a mix of globules. However, it will separate. This is because water molecules will attract and it will separate the oil, i.e. squeeze that out. Dispersion of immiscible liquid is shown in this slide. Emulsion is a dispersion of one miscible liquid into another miscible liquid. Dispersed phase is a globular phase, it's again called internal phase. Continuous phase is a external phase of the liquid. In the slide on the right-hand side, you see 3 test tubes. First test tube has an oil drop and the water or aqueous media colored blue. Second test tube shows an emulsion formulation of a globule. And if we do not have anything else in that system, it will separate as an immiscible liquid. So, what we are interested in cosmetic and pharmaceutical uh, product development is how do I stabilize immiscible dispersion? Emulsion is a biphasic dispersion of immiscible liquid. To create a stable emulsion, that means the globules do not collapse on each other. Emulsifiers are needed. Emulsifiers are chemical substances that prevent separation. But emulsifier alone does not do it. We need to provide an energy to disperse liquid to create emulsion. So two things are needed. Let's look at emulsifier. Mediator compound that keeps immiscible liquid held together. They do not make solution. They hold immiscible liquids together. Emulsifying ingredient molecules have a hydrophilic and lyophilic end that attracts aqueous and oil phase respectively. In addition to that, we must provide an energy. A relatively large amount of energy is required to break dispersed phase liquid, for example, oil, and disperse it into evenly throughout a continuous phase such as water. In addition to that, agitation time, how long do you mix, rate of addition of these media, temperature, all those factors play important role in forming and stabilization of emulsion. Emulsifiers, physiochemically, emulsifier have unique property. They have a hydrophilic water-soluble head, oil-soluble tail. Lyophilic end attaches to oil, i.e. that portion dissolves into oil or mixes into oil. Hydrophilic and water loving portion of it remains into water. On the interface between water and oil, emulsifier distributes itself and it prevents oil droplets from agglomerating, i.e. breaking of an emulsion into two phases. Three most common types of emulsifiers are anionic, cationic, and non-ionic. Anionic emulsifiers, such as sodium dotacal sulfate, has a negative charge on its main body. Cationic emulsifier has a positive charge, as shown here, citramonium bromide. Polysorbate 80 has a shorter tail and a very big end or a head. And most commonly used emulsifier is non-ionic. Emulsifier have interfacial properties, i.e. between the interface of water and oil. That's where they act. They're also called surfactant, and they reduce the surface tension of the oil-water interface. Let's look at a couple of simulations. Emulsifiers have two ends, hydrophilic and hydrophobic. Water-loving and dislikes water or oil-loving. When we add emulsifier, what we see is emulsifier attaching at the interface of oil and water. In this case, it's oil droplets and water as a continuous phase. So emulsifier will embed and it would start repelling each droplet and thereby stabilizes emulsion. So key concept is to prevent droplet from collapsing on each other or coalescing on each other. And emulsifiers are necessary to do that. If we add oil into water, and as you can see here, there's an oil and water added, and we can mix it, provide mechanical energy, uh, it will not form stable emulsion. It would separate because of water will squeeze out the oil. If we add emulsifier to the mix, would it make emulsion without providing any mechanical energy? That's a question. And we will see that we add emulsifier to it. It does not form emulsion. It sits. So we now have a three phases: water, oil, and emulsifier. If we provide mechanical energy by just mixing it, you will see a emulsion preparation. Oil droplets, non-polar tail is incorporated into oil and polar head remains outside. This forms an emulsion. So from a physicochemical perspective, we need the right type of emulsifier that will allow it to uh, solubilize the tail portion into oil, the head portion into water, and a mechanical energy. Emulsifiers have hydrophilicity and lyophilicity. So there are many compounds that have hydrophilic and lyophilic nature. And they can be used emulsifier. However, it depends on the continuous phase and the ratio of oil to vehicle or aqueous phase. If hydrophilicity of the molecule is much greater than lyophilicity, molecule will disperse into water as shown in A, and it will not emulsify oil-water mixture. Similarly, if the lyophilicity of the emulsifier is much higher than hydrophilicity, it will not form an emulsion. It will disperse into oil. So using incorrect emulsifier will not make an emulsion. However, if hydrophilicity and lyophilicities are balanced, as shown in the middle figure, where on the interface of the oil and water, emulsifier orients correctly, in that case, it will form stable globule as shown in the figure below that. This is physiochemical principle. In the next module, we'll continue our discussion on physical chemical properties.